we can all watch the messiness of all of this. So the last chemistry that we talked about was protection chemistry, that is acetal formation. And the thing you would have seen from that I think the recording is not going to pick this up. So if you're watching this after the fact, it doesn't make any sense. Apologies. You want to feel super self-conscious, by the way, record yourself talking to a whole bunch of people close up. It's awesome. Okay, there we go. This is the protection chemistry that we talked about. So in this scheme, can you see my, okay, you're going to be able to see my cursor on a recording. If you're watching this, you cannot see my cursor. I have two different functional groups in this molecule. One is an ester, one is a ketone. Ketones are more reactive than esters. So the first thing I would do is, if I wanted to reduce this molecule, let's say I added lithium aluminum hydride to it. If I wanted to try and reduce the ester, but not the ketone, that wouldn't work because lithium aluminum hydride would reduce both of these moieties. I would get an OH over here and I'd get an OH over here. That's chemistry we've seen before, right? Turning one, in this case, it'd be one addition of the hydride here and two additions of the hydride here. So that would make a primary alcohol and a secondary alcohol. Reduction of an ester, reduction of a ketone. I don't want to do that. I want to mask the reactivity of the ketone so that I can only react the ester and then run the reaction I want and then unmask the ketone later on. You can literally think of this like masking tape. If you're going to paint a room, one of the things you do is put up some masking tape, paint over the area you want, so you don't get paint on this part, peel the tape off, and now you have a clean surface. We're going to mask this ketone with this molecule, ethylene glycol, make this molecule, which is an acetal. With the acetal there, I can run this chemistry now. The lithium aluminum hydride will not react with the acetal. It will react with the ester. Do that reduction, clean it up to get to the primary alcohol. H3O plus and heat turns my acetal back into a ketone. Protection, run the reaction I actually want to run, deprotection. Apply the masking tape, paint, unapply the masking tape. That's quick. Is that helpful at all? Okay. Now the actual mechanism of this is long, right? So there's a lot to learn. Yeah. So here, if you look at this, I've got an OH here and an OH there. That oxygen has two carbons. That oxygen has two carbons. This molecule is that. The molecule in blue is the molecule in blue there. It's just rotated over. Yeah. I think it looks like a little like praying mantis face. Yeah. Anybody else? That's a good zoom in. Feeling good about that. Feeling confident. I'm gonna get rid of that right now. Yeah. Ethylene glycol. What about it? Right? Isn't that messed up? So ethylene glycol is a misnomer using the IUPAC naming convention. It is a diol. Why we call it ethylene glycol is beyond me. It's kind of like why we call petrol gas. That's messed up, right? It's a liquid. It is not a gas. It'd be a big problem if it was a gas. If you go to the pump and you squeeze the handle and gas or a gaseous mixture of alkanes poured out, you would explode. That's an issue. So we do this a lot with common names for molecules. Ethylene glycol is a common name. Okay, so I looked at my notes and I was like, well, where are we going to start off after this emotionally wrenching week that we've been through? And it's on a very complicated reaction. So welcome back. Missed you all. We need to talk about section 19.11 because the universe has a sense of humor, which is about phosphorus ylids. This reaction in particular, so that's already complicated, right? Phosphorus, haven't used that in a long time. Ylids, what in the world is that? This is a type of reaction called a Wittig reaction. Now he said Wittig and then wrote a W. What is up with that? I have been teasing the German language for some time now, and then I had a student that was like, no, Americans have it wrong. Because if you think about it, a W is two U's, right? So a W should have like a sound to it. A W like this is two V's put together, right? So the German pronunciation of W's with V's, like Volkswagen, makes more sense. So you just take the W, split it in half. This is the Wittig reaction. That's how you pronounce that. The Wittig reaction actually has very simple products. It just goes through a complicated mechanism. So let me show you the simple part first. It is going to be the reaction of an aldehyde or ketone with this thing. It's called an ylide. This is a little confusing. This P is a phosphorus. The pH, does anybody remember what pH is? Phenyl, that's a benzene ring. So this is triphenylphosphine. I'll write all that down here in a second. But when you have a carbon phosphorus double bond like this, that is called an ylide. All right, so big and scary, right? It's big and don't act all tough. It's big and scary. Oh, fine. So the reason that Ren's not freaking out over there is he knows that whenever you see a ketone, when you see a carbonyl with an ylide, you're going to cut the ketone in half. You're going to cut the ylide in half, and you're going to just drop that carbon-carbon double bond on top of the carbon-oxygen the carbon on this side onto the carbon on that side to make a new carbon-carbon double bond. That is how we turn an aldehyde or a ketone into an alkene. The other thing that we're going to make here is triphenylphosphine oxide. So I don't need you to know so much about the triphenylphosphine oxide. I will show you how that's formed. But really what we're going to do here is make a carbon-carbon double bond. And that's unique because there wasn't even a carbon bond here. It's not like I'm taking a carbon-carbon single bond and making a double bond out of it. That's an elimination reaction. This is just wholesale creating a new carbon-carbon double bond. And after 2 weeks of us not meeting and talking about this, I know you are just dying to know how this reaction works, and I won't leave you hanging anymore. Let's talk about the really scary mechanism of the Wittig reaction. I drew the ylide like this as a double bond. And actually, I'm gonna go ahead and draw. Oh no, we'll leave it as acetone. What I'm going to do is draw a resonance structure of the ylide where I have a carbon phosphorus single bond and a lone pair of electrons on top of the carbon. That would give the carbon a negative charge. Oops, let's move this over. And the phosphorus a positive charge. Does everybody see how this is a resonance structure of that? I just took this double bond and I moved the electrons onto the carbon. Now I have flipped it over, and I'm sorry about that. I'll show you why I did that here in a second. But I just moved the double bond here onto the carbon. That's why this structure that I drew in black is a resonance structure flipped upside down. You see that? This is the much more stable way to draw an ylide. This is how they'll be presented. The reason I'm drawing it like this, though, is that that leads to the reactivity the ylide is going to show us. I have a carbon nucleophile. Is there a place that this carbon can attack? Is there an electrophilic site somewhere, say over here, at the carbonyl carbon, right? So we see this a lot with chemistry that we have not spoken about, but you watch me yammer on about from last semester, where a nucleophile attacks that carbonyl carbon. What's next? You're going to move the double bond up to the oxygen, which is going to make a what? A tetrahedral intermediate. Tetrahedral intermediate. Yeah. There. So I heard two correct answers. This is both an alkoxide. That's an O minus attached to a carbon. It's also a tetrahedral intermediate. This type of molecule where you have a positive and negative charge that are right next to each other is called a betaine. The only reason I'm telling you that is the MCAT loves to talk about betaines. Guess why? Because they look big and scary like that. That's the only reason. They're not that important, but there's something about having these positive and negatively charged oxygen and phosphoruses next to each other. Phosphori, phosphoruses. When you put a positive and negative charge next to each other, we call that a betaine. It sure would make sense if this minus would attack that plus, right? This is just old pass and catch football, right? So negative charge here attacks that positive charge there. That's going to happen to make this four-membered ring. I'm going to keep labeling these two things just to keep an eye on them. This molecule has its own special name. No, you don't. You sure don't. This is called an oxaphosphatine. Guess if you need to know that name. You don't. Guess why I'm telling you. The MCAT. Yeah. And by the way, where you're going to see this in the MCAT is whenever they give you like a page of information where they're like, come read a story about organic chemistry and then answer a question that has nothing to do with what you just read. It's in that question where you'll see this. Freaking hate that exam. I guess it somewhat keeps me in work, but horrible. Okay, oxaphosphatine. How do we feel about it? Besides the fact that it's got a big scary name and it's got phosphorus and all this other stuff. Bad. Why don't we like it? Yeah, the bond angle. So the ideal bond angle of an sp3 hybridized carbon is 109.5. The bond angle is right chump. Not 109.5, 90 is the square, right? So right angle, not good, compressed. So this molecule wants to fall apart. It's the formation of the oxaphosphatine that makes this molecule break apart. And in this next step, that's where the carbon-carbon bond is going to form. What happens is the carbon-oxygen bond is going to break up this way, and the carbon-phosphorus bond is going to break down that way. That's going to lead to a double bond here. Put a box around that because that's our alkene. And then the other thing we're going to form is that triphenylphosphine oxide. You see it? Mm-hmm. You gonna go back to the recording, Dr. Green? With that dude, you could push pause. You'd be like, please stop speaking. Like, turn me off. I think this reaction is pretty exciting. Not only did we form a new carbon-carbon bond, but it's a new CC double bond. I haven't shown you how to do that before. We've made carbon-carbon bonds, and then you know how to functionalize them and then do additional reactions. But we wholesale just swapped out a carbonyl for a carbon-carbon double bond. Those are strong bonds. This is a very important reaction in the formation of carbon-based structures. And fortunately, we can control this ylid pretty well. So let me show you how to make the ylid, because if you know how to make the ylid, you know how to make lots of different alkenes in place of aldehydes or ketones. But before I do that, any questions about any of this nonsense on the page? This morning, I was asking my students if they were like, okay, or if they were worried about me. And I think more, it's just like automatically shifted. You're like, okay, he's fine. I'm not worried about myself again. This is terrible. All right, first things first, I'm the illid. That joke never works. And apparently it's realist, not illest, but I still like it anyway. Here's the reason why the illid is so fancy. You already know. You can take the triphenylphosphine. I'm telling you, that joke used to slay when that song was popular. Now nobody knows what I'm talking about at all. Whatever alkyl halide you want to start with, let's make this green. You can start with any alkyl halide you want. Whatever is attached to this halide, that's what's going to get attached to your phosphine. That's what's going to get attached to your double bond. This thing attacks that thing, kicks that off, forms this molecule. Now, this is not an illid. I need to lose a proton from this to make the illid. Here's where things get super freaking dangerous. We have to use a very, very strong base to pull a proton off of this molecule. The base that we're going to use is called N-butyl lithium. I think I've brought this up before. That sound familiar? N-butyl lithium? No? Okay. It is a very strong base. Back in my day, when I was an undergrad, not undergrad, when I was an early graduate student, there was a young researcher, I think at UC Irvine or Riverside, I forget at this point, that was pulling some N-butyl lithium out of a syringe. She was working in a vent hood, and she was pulling on the syringe, and the syringe it's pretty sticky material, so she was having to pull on it pretty hard. The back of the syringe pulled out, and some of the N-butyl lithium got out of the syringe and fell onto the bench top. There was some organic solvent on the bench top, and this stuff reacts so strongly with it that it set itself on fire pretty quick. She panicked, kind of threw her hands back, knocked over a larger bottle of that material, set that on fire. Don't laugh, she burned to death. So yeah, it was rough. So there was the PI of that lab went to prison for criminal negligence of like trying to put this thing together, of trying to keep a lab safe. We don't work with N-butyl lithium very much anymore these days because of that. That is a really like sad example. I actually did work with N-butyl lithium at the time, and then we stopped whenever the, death thing happened. So, sometimes I'll joke around about how strong molecules are. This one, literally, like if you have a bucket of water and you drip it into water, it can't set the water on fire, but it's going to try real hard. You'll see it spark and steam as the drips hit water. The reason you need it to be so strong is these protons are not acidic whatsoever. The negative charge here has to really want it to take off one of those protons. This is an alkane equivalent. So that ends up giving us our illid, the negative charge here. Now, again, we don't draw the illid that way. It's preferred to show the illid as its resonance form. This is, I think, the most helpful way to draw it because you see the negative charge on the carbon. It can be, yeah. This thing, oops, that's not supposed to be right. This thing is the illid. shouldn't have brought up the UC Irvine death thing. I like barely had you there, and then you're like, man, you brought it down again. It's like Dr. Doom and Gloom up here. I think there were some valuable lessons for me at the time. It was shocking when this happened. Like that, like deaths in a research setting should not occur, right? That's the whole thing is we put all our variables in. That's like 1950s, 1940s stuff when they were like pipetting by mouth. Those guys didn't make it, right? And then you go, well, that makes sense. You were drinking chemicals. Stop doing that. In the 2000s, that just shouldn't occur. So it's not that n-butyllithium is such a horrible thing. It's that when we work with molecules of concern, we need to treat them with respect. And so that's one of the things I hope to get across from this is there's nothing wrong or evil about n-butyllithium. There's something wrong about working with n-butyllithium with a gallon of cyclohexane next to you, right? That shouldn't occur. You have a fire source and a lot of fuel in one space. The researcher was also wearing a big fuzzy knit sweater and no lab coat, right? So multiple things went wrong there that did not work out very well. I think the professor that got arrested was later acquitted, but it was or later had his record expunged, but it was a big deal. So anyway, happy story about that. Questions about how to make an ILID? Great. I can tell that some of you were looking at this screen going, well, who cares, Dr. Green? I can make double bonds. I know how to do that. I can take, say, a carbonyl and react it with a Grignard reagent. And then POCl3, phosphorus oxychloride, and pyridine. So this one would make a tertiary alcohol, right? Methyl Grignard attacks there, that would turn into an OH. Then POCl3, what does that do to alcohols? Huh? I will have to remind you. Once one of your peers reminds me, it doesn't reduce it. POCl3 does what? Doesn't turn the alcohol, that'd be thionyl-chloride, SOCl2, very close. Same chapter, a little bit later. Wah, wah, wah. It turns alcohols into alkenes. POCl3 eliminates alcohols, which is why it is possible to make that, but you'd also make this. Which one of those two alkenes would be your major product? The second one says who? Zaitsev. There we go. We're back. You would form this, but you would get 90% of your product would be this, because Zaitsev says if you're going to make a double bond, you're going to make the more substituted double bond in almost every situation. Well, what if I want this one? What if that's the one that's going to cure cancer? Is there a way that we can form that more directly? We could do a Wittig reaction. React that with Wittig. I'll write a CH2 up here just so you can see it together. This would be 84% yield. So it's not perfect. This molecule is pretty reactive. You would get 84% yield. It would not form any of that. The reason it doesn't make 100% product is not all of your ILID is going to fully convert because it's very it's a very strong base as well. So you have to worry about it falling apart. So if you want to be more selective with where your double bond shows up, if you want to make a non-Zaitsev alkene, the Wittig pathway is a good way to go about that. That was with me. No, so what I'm showing is the Wittig has already been formed. Okay. Right, so up here, I was preparing the ILID. Once you have the ILID, then you can add it in. Right, so I won't you can see that you can be asked the chemistry about how to prepare an ylide, but it's also very common because the Wittig reaction is its own thing to see a carbonyl compound with the ylide already formed. You would need to make this in situ, just like if you are in the lab and you ran the Grignard reagent, you have to make that in place. You can't just put Wittig on the shelf. It's too unstable. So you have to make the ylide and then use it. But if you're given this, you just go straight to the product. I know it's a very complicated reaction for our first discussion in 2 weeks. I'm sorry. Which is why I'm going to skip over section 19.12. It's about bioreductions, and anything that has bio in here is like kind of biology. So we're going to talk about conjugate additions instead, because we're going to focus on real science. Yes, you can tell your biologist teachers I said that. Conjugate addition. To a particular type of aldehyde and ketone we call alpha beta unsaturated carbonyls. It's probably a trash call, but who knows these days? Hi, this is Nathan. Yeah. Hey, Rondo, can I call you back in about 20 minutes? Thank you, sir. Bye. To carbonyl compounds. Okay, so alpha beta unsaturated carbonyls. These are molecules that have a carbonyl, and then as we count away from the carbonyl center, this is the alpha position, that's the beta position. If it's unsaturated, then there's a double bond there. So this is an alpha beta unsaturated carbonyl. I forget if we've talked about counting away from carbonyls with the Greek alphabet before. No. We have? Okay, good. So that's not a new idea, right? Yeah, acrolein. An acrolein derivative. Yep. Okay, so I think, yeah, let's go through this. We have been talking about, or in the recordings, we've been talking about having a carbonyl compound where a nucleophile directly attacks the carbonyl carbon. That pushes the electrons onto the oxygen. And then later on, this takes a proton. This is what we call a direct addition. Before, I was just calling it an addition to a carbonyl. We had a nucleophile attack the carbonyl carbon, and then we'd make some tetrahedral intermediate. When we have an alpha beta unsaturated carbonyl, the nucleophile has an option. It can attack the carbonyl directly, but the nucleophile can also attack the beta carbon. And the reason it can do this is that the beta carbon is electronically connected to the oxygen via resonance. Double bond, single bond, double bond, which means if the nucleophile attacks here, I can push the electron density onto the oxygen in a similar manner. I just have to go through one more step to get it over there. That allows for this molecule to have a new bond over here. And then that will take a proton. And the reason I'm going to show you a proton here, hopefully will make sense in a second. I should have. Sorry, guys, I should show you a proton up here too, because I'm about to do some counting. It's going to be confusing if I don't do this. Sorry, I know Mia Racing is not super helpful for you. Let's add a proton up here as well. My bad. Okay, this is still my direct addition. This is what we call a conjugate addition. Sometimes the direct addition is referred to as a 1-2 addition. The reason we call it that is the nucleophile added to carbon 1 and the proton added to atom 1, atom 2. So there was a new bond here and there's a new bond here. We call that a 1-2 addition, or 1-2 adduct is how it's sometimes referred to. In the conjugate addition, the nucleophile added here, so 1, 2, 3, 4, the hydrogen added over here. We call that a 1-4 addition. Now you're probably familiar that this type of molecule is not super stable. What does this look like when you have an alkene and an alcohol? What's that called? An alkene alcohol? Enol. We know that enols, what's that big word? Tautomerize into this. So often conjugate addition products are going to look like this. It's just a little harder to see that it was a 1-4 addition because then they moved around to make this final product. Most nucleophiles exhibit a preference for direct addition. So some nucleophiles we've talked about: hydrides, Grignards, O-, C- for that matter. Grignards, a C-. All of those prefer to attack in this sort of fashion, where the carbonyl gets attacked directly. This molecule could be attacked directly as well. I'm just showing you it attack the beta carbon, but a nucleophile could, if it wanted to, go straight here, right? It doesn't have to attack the beta carbon. Most of the nucleophiles we've talked about attack the carbonyl directly. I'm going to tell you about 2 nucleophiles that like to do this kind of addition, where they attack the beta carbon. And that might be helpful in separating out what type of attack you're going to see from what type of nucleophile. Yeah.
Why is that? Why is that possible? We haven't seen like a third carbon.
Yeah. So if you count it, it's not just the carbons; it's the number of atoms. 1, 2, 3, 4. Nucleophile added there, hydrogen added there. Here, 1, 2, nucleophile added there, hydrogen added there. It's a good question. The hydrogen on the final product, I didn't show you tautomerize it, but if you look at this, there's 1 hydrogen here. There's 2 down here. So that is what a tautomerization is. You break an oxygen-hydrogen bond and replace a carbon-carbon double bond with a carbon-oxygen double bond. So they kind of swap places. I'll show you a mechanism here in a second, how you can go from this, which doesn't have a charge, there you go, to this directly. Actually, here, I'll show you on this molecule. Maybe don't write this down because it's too many arrows. But if you want to go straight from here to there, what you can do is push the electrons down and then pick up the proton that way. You can kind of think of it like that, right? Where the O- is pushing its electrons down, and then the alpha carbon here is picking up the proton. That's a little bit more direct route. The reason I'm showing you this molecule is it's more obvious to show the 1-4 addition. Nucleophile added here, hydrogen added there, 4 atoms away from each other. Ish. Okay. Sometimes I bring up material in chem and I'm like, it's hard, but we're doing okay. And then other times I'm like, okay, now we'll just go on to the next topic, see if they notice. There are two different types of nucleophiles I want to show you about. One of them is amines. Amines prefer conjugate addition. There is an alpha beta unsaturated carbonyl, all packaged nice and neat. If I add in a primary amine under acidic catalysis, this nitrogen is going to add, this nitrogen is going to add at the beta position. If it added directly, let's see who's been watching these lectures, because this is like the beast of a topic. A primary amine plus plus a ketone makes what? Enamine would be with a secondary amine. What's the other one? Imine. Amines can make imines or enamines. Simple. How can you get this confused? This is the sole product that's formed. Or as I always like to call it, the sole product. What is not formed is the nitrogen attacking directly, because if it did, that's what it would look like, which you all correctly identified as an imine. If you have no idea what I'm talking about in this red box, if that looks totally foreign to you, may I recommend one of the videos that I so dutifully recorded last semester when times were simpler and better about how to form imines and enamines from amines. I think I even have a whole thing about how to talk about that. This is not formed. The reason it's not formed is this would be a direct addition. And an amine will not undergo a direct addition if it has an alpha beta unsaturated carbonyl. It will attack the beta position. This is the thing that's going to form. I feel like we need to try this. Come on, handwriting. What do I form on the left? What do I form on the right? Any brave souls or people who just don't give up anymore? I'll take either. Tertiary alcohol on the right. I love it. So would that be a direct or a conjugate addition? Right? It'll be a direct because we have a very direct professor and nucleophile. So the CH3 here is going to attack right at the source to make a tertiary alcohol. And can I just say how I love you refer to it as a tertiary alcohol? Ah, my man. Anybody else on the left? This would be a direct addition. How about that there, nitrogen? Jayla's got a thought. She does. I knew you. I knew it. Yeah. So let's use our big fancy words. Which carbon is it going to attack? Wait. Are you going to attack this carbon, that carbon, and that carbon? 1, 2, or 3? Third one. That would be the alpha beta. We're going to attack the beta carbon. So I agree. We're going to make a beta addition. That means my new bond is going to be here. What's going to be attached to that position, Jill? The nitrogen. And what's attached to the nitrogen? 2 methyl groups. I change it up on you. Move this down. Fantastic. Is that a direct or a conjugate addition? That was a conjugate addition. It loses the hydrogen through just a basic catalysis removal. Remember that amines themselves are basic, so you don't have to put in a dedicated base for this. A conjugate will always be 1,4. A direct will always be 1,2. Yeah, so you'll see me use those interchangeably. Yeah. Because amines prefer a conjugate addition. So the reason why is it's a mismatch of how much electron density is on the nitrogen and how much electron density is not on the carbons. If you were to map out the electron density here, there'd be a big partial plus here and a smaller partial plus here. So if you're a nucleophile, this is really where you want to attack. That's the carbon that's lacking the most electron density. But it's also sp2 hybridized, which means it's trigonal planar. It's a little bit more crowded in there. Here, we can get to this carbon, generally speaking, much more easily. So these beta additions are easier to approach, and what we call a softer nucleophile is more likely to go for them. A hard nucleophile is one that has electron density packed in around itself really tight, like a billiard ball. A soft nucleophile is more like a volleyball or a beach ball. It's got its electron density is a little bit more diffuse, which means it's a little more stable, and it can be more patient about where it's going to attack. So they tend to avoid these more sterically hindered sort of situations. Amines aren't the strongest nucleophiles, so they tend to attack beta. Another example of this that I will bring up is the Gilman reagent. So Grignard, I just showed you, is a carbon nucleophile, and it adds direct. You might recall from OChem 1 that we talked about Grignard reagents and Gilman reagents at the same time. We haven't talked about Gilman reagents since that time, but they're back and they're important because the Gilman reagents only have 1 minute of time, apparently. If I'll just show you the reaction here. If I take that same molecule and I react it with a organocuprate, so that is the Gilman looks like this. It is a carbon species attached to a copper lithium species. So this is a copper with 2 methyl groups, has a negative charge. There's a lithium counter ion to it. We do this in two separate steps. So if you look at this, it should look familiar to you as a Grignard reaction. If I just switch this out for MgBr up here, you can think of them in the same way. Whatever's in the parentheses is a carbon minus. You think of this like a methyl, the negative charge. Except the Gilman is a softer nucleophile. It's not as strong as the Grignard, which means I can get this to react down here. Gilman reagents prefer conjugate addition. Well, now you have yourself a powerful set of reactions, because if you have an alpha beta unsaturated carbonyl, you get to decide if a carbon is going to attack here, you'd use a Grignard reagent, or here, you'd use a Gilman reagent. And based on which one you choose, you get to pick the regiochemistry of that new carbon-carbon bond you form, which is hugely important for stereospecificity and regiochemistry for lots of different things. We'll leave it there for now and pick up with spectroscopy on Wednesday. Good to see you all.